For our second lab report, we decided to investigate viscosity. For our research question, we wanted to look at how the density in a given solution, specifically changing the density of a given solution, affects the velocity of our object, which in this case was the metal ball bearing. Our main goal was to determine the relationship between that viscosity and different densities and look at the observable trend line. Take a step back real quick as to what viscosity actually is. Viscosity can be defined as the measure of resistance as an object moves through it, specifically a fluid. We initially predicted that ball bearing falling through our given cylinder would move fastest through air and slowest through corn syrup, as corn syrup is much denser than air. And these interactions between the metal ball bearing and the different molecules in the higher dense corn syrup would then slow it down as through friction. This was in fact correct, and the results were confounded by our data. And we found that it is indeed true that the increase in the density of the fluid will increase the force of viscosity due to the interactions of particles on the molecular level. So what exactly changed? Well, we looked at both air, water, and corn syrup for our experiment, as you can see here. These weren't our trials, but this is just a representation of what we actually did and the different solutions and densities that we did. For our trial, while many different factors could have affected different viscosities, we decided to keep the object surface area and the initial velocity all the same. The only thing we specifically looked at was density. As such, we dropped everything to the same height and made calculations based on the same distance apart, keeping everything at around 40 milliliters and about 5 inches. In our experiment, we decided to have 3 trials and to record 2 videos for each one of those trials, the first being air, water, and then corn syrup. We then inputted this into a tracker, we calibrated it, and then tracked position across the ball bearing falling through each of these substances, and that gave us velocity. We decided to change our density between all 3 fluids, which was obvious, and then that gave us a different velocity constant for all of those, which we used for our results, and then that gave us the trend lines we were looking for, which then says that an increase in the density does in fact give us an increase in the viscosity constant. But prior to that, we also had to find the distance fallen, we had to calculate terminal velocity, and then we also had to calculate density, specifically the density of the given ball bearing as well. Everything else we researched on our own. Here are our system schemas and free body diagrams. You can see in our system schema that the ball bearing was acted upon by contact in the solution, specifically the air, water, and corn syrup, and had the gravity acting upon it. Well, we chose to have our system as within the solution and the ball bearing. And for our free body diagrams, initially, when the second we released it from the hand, there was only gravity acting on the ball bearing, but once the ball bearing was in solution and reached terminal velocity, there was the viscosity force acting on the ball bearing, trying to resist it through friction, and then there was the gravity acting downward on the ball. This is just a quick model explaining what we actually did in our experiment and how we tracked it. Back to the calibration stick, this was the initial height at which we dropped it, trying to keep it as consistent as possible. We found that the ball bearing mass was around 8.3, which is very valuable in us calculating its density. It's also key to understanding what friction actually does in this scenario. Friction is very important when we're talking about viscosity. At a molecular level, viscosity is the result of the interactions between the ball bearing and the surrounding molecules, which simply states the friction between those 2 molecules.
Okay, for velocity graphs for air, you can see this is where it was dropped and this is where it hits the bottom. For our second trial, this is where it's dropped and this is where it hits the bottom. For a water graph, you can see that this is where it's dropped and this is where it hits the water. This is also where it's dropped and this is where it hits the water. And for our corn syrup graph, this is where it's dropped and this is where it hits the corn syrup, and this is where it's dropped and this is where it hits the corn syrup as well. The equation we use is a dynamic viscosity equation, which is 2 times the change in density times gravity times radius squared divided by 9 times terminal velocity. And as you can see, air had the lowest average viscosity constant, water had the second highest, and corn syrup had the highest viscosity constant, meaning that the higher the density fluid will increase the more force of viscosity, which is due to interactions of particles on a molecular level. There could have been error due to possible tracking error as well as like error of dropping the ball and whatnot, but as you can see, our hypothesis still stands that the higher the density, the more viscosity constant will show. Thanks.